We introduce our work, AutoSDF, a way to learn shape priors and leverage them across various conditional inference tasks. Simply put, we wish to generate plausible 3D shapes that agree with the given conditioning. We target the tasks of shape completion, language-based generation, and single-view reconstruction. Conventional approaches target them independently. However, these three seemingly different tasks are all trying to predict a plausible distribution over shapes. Hence, our thought is, what if we can first learn a generic understanding of the geometry of 3D shapes and then leverage it across these tasks? Learning a distribution over shapes implies we need to learn a distribution over some volumetric representation like the truncated sine distance functions. But first, we need to reduce this volumetric TSDF representation into a compact and discrete latent space such that we can approximate the distribution over shapes as a distribution over latent tokens. This enables us to leverage powerful neural networks with limited memory. We use the VQVAE framework with an encoder-decoder architecture to find a latent representation together with the vector quantization step for discretizing this latent space. We introduce a modification wherein we split the shape into uniform small cubes and encode them independently. We do this to facilitate shape completion, as different input conditioning will activate corresponding regions of latent space. We then decode jointly to map back to the space of 3D objects. Here we visualize some shapes auto-encoded by the VQVAE and find that it can faithfully capture the global geometries of objects even with significant compression. We then use the autoregressive formulation to model the distribution over this grid-like symbolic space. We factorize the entire distribution as a product of the likelihood of observing a query token given already observed tokens. We use transformers to model this distribution. Since input conditioning, especially for the shape completion task, can come in any order, we shuffle the order of observed tokens and use a query index at every step to impart order invariance during training. Here are some results for unconditional generation, which highlight that the proposed method can generate diverse shapes. Our model also naturally allows us to perform shape completion. And since we model a distribution, the approach supports multimodal generation where each sample agrees with the conditioning. Our approach also fares well when compared with certain recent baselines. The task of language-based generation and single-view reconstruction can also be reduced to predicting the distribution over symbolic grids. However, unlike shape completion, the conditioning input now is much more generic and cannot directly be reduced to observed tokens. Hence, conditional inference is a complex function and may require a lot of pair training data here. Instead, we factorize the per step probability in autoregressive formulation into a product of two terms. First, the likelihood based on past observations, and the other based on input conditioning. With this factorization, the first term is the same as our proposed shape prior, and for the second term, we use domain encoders to parse the conditioning followed by a decoder to map to the space of our symbolic grid. To analyze it further, we parse the conditioning with domain-specific encoders like ResNet and BERT, and we predict a symbolic 3D grid where at every location, in one step, we predict the categorical distribution over tokens. During inference, for every location, we sample from the product of this distribution and the one from our shape prior. Here we visualize some results for single view reconstruction, wherein we observe that where the conditioning is much more informative, the results are close to each other. However, when the input is ambiguous, the generations are diverse, defecting various possibilities, while still agreeing with the basic information that the image is one of a revolving chair. Similarly, when compared with other baselines which effectively do not leverage the proposed prior, our method performs fairly well. We include some quantitative results as well. For the task of language-based generation, we observe that the generations from our method align very well with the input, while also being fairly diverse. When compared with a recent baseline, which learns the joint distribution without our proposed split, we observe that the shape do not align with the input very well. This is also true when compared with the other baseline. We have released our code for AutoSDF, and for more details, please visit our project page. Thank you.